So today I'll talk about high frequency scattering problems. Initially, I'll focus on, so I cannot proceed to the next page, interestingly. Let's see. Maybe I can proceed in this form. So you can see you can still see the screen, right?
Yeah.
The outline of my talk is I'll introduce first the high frequency scattering problems I'm working on. I'll talk about integral equation methods for single scattering problems, and then I'll introduce the formal Neumann series representation of multiple scattering problems. This will lead into our ongoing work on Ray-stabilized Galerkin boundary element methods for multiple scattering problems. And time permitting, I'll talk about also on ongoing work about the high frequency scattering amplitude. So the problem I'll talk about today is comprised of the Helmholtz equation. So you are given this instant field satisfying the Helmholtz equation on the entire space. And we are looking for the scattered fields satisfying the Helmholtz equation in the exterior of an obstacle, right? Here, omega is our obstacle. And for the purpose of this talk, initially I'll assume that this scatterer, omega, is a convex obstacle. Although almost all the formulations you will see are valid, integral formulations are valid independently of that. So I'll look at two types of boundary conditions, right? The classical ones, Dirichlet and Neumann boundary conditions. And to ensure uniqueness, I'll assume that, right, I'll also demand that the radiation condition is satisfied. For high frequency scattering simulations, basic challenges on the numerical side is that the fields oscillate on the order of the wavelength, and this when high frequency applications are considered, this is not treatable using classical numerical methods. They are, as I have written here, they can be grouped into several different approaches, including variation methods, differential equation methods, integral equation methods. But as I said, I'll be talking about high frequency scattering problems. So in that case, asymptotic methods are quite handy. However, asymptotic methods are unfortunately not convergent because they solve an approximation of the PDE at hand, not the actual PDE. So recently, when I say recent, in the last 20 years, the most successful approaches have been based on a combination of integral equations and asymptotic methods. That's what I'm going to motivate and show you the details about today. So I'll denote by U the total field, right? U instance is already given. We are trying to compute the scattered field, which is equal to computing this total field. In this case, the fundamental solution of right the Helmholtz equation in 2 dimensions. Right, we could also work in higher dimensions, but just to mention, in 2 dimensions, it is given in terms of an Hankel function. Right, classical integral equation theory then tells you that in the case of the Dirichlet boundary condition, which is also known as the Sanhart scattering problem, the scattered field is given as this singular representation, where eta here is the normal derivative of the total field. Right, so this integral representation therefore tells you that in this case, computing the scattered field demands the computation of the normal derivative total field on the boundary. When you consider the Neumann boundary condition, which is also known as the Sanhart boundary condition, in this case, the scattered field admits a double layer representation, and the new unknown in this case is mu, right? Mu of yk, which is the total field on the boundary of the scatter this time. So looking at right, so and these unknowns, right? Eta, the normal derivative of the total field, written in red here, can be represented as the solution of certain integral equations. And there's an extended literature on generating well-conditioned, uniquely solvable, blah blah integral equations. I'm just writing here a basic integral equation. And what I'm plotting here, right? There is an obstacle omega on top right. I'm going to assume that it is a unit circle, and I'm going to take an incident field coming in from the left as plotted in that figure, and then I solve this integral equation, right, numerically, and see that the real part of eta modulated by k, as plotted on the left, is highly oscillatory. Similarly, the imaginary part behaves in a similar way. But as you see, the solution decays. The solution decays on some part of the boundary to zero, right? It looks like it is zero. And on one part of the boundary, it is not zero, it is highly oscillatory. Geometrically, what is really happening here is, if you look at the figure on top right, there's a scatter omega, and the instance is coming from the left. And there are three rays, right? There are actually infinitely many rays. This is a plane wave coming in from the left. And these rays will be tangential to the boundary at the bottom and at the top points of the scatter here. So beyond that, if you think of this plane wave as a light source, right, coming in from infinity, what is really happening is there is a shadow part of the scatter in the back on the right-hand side of this plot here, right? So that in that part, you would expect that if this was a light source, then that part would have been dark. And going back to the plots down there, actually, right, the solution seems like zero. So this is really quite in agreement with the physical intuition. These parts must be dark. And this part I'm going to call the illuminated region, right, on the left. And the part on the right of the scatterer will be called the shadow region, right? And the physical intuition, maybe not so mathematical, but the physical intuition tells you that if you know the oscillation of the incident field, the density change on the boundary of the scatter should oscillate along with the incident field, right? So with this in mind, right, this is the plot for the Sanhart problem, right? Similar behavior, the solution oscillates in the limited region, and it vanishes on the, it maybe in a different manner, but on the shadow region. So as I mentioned, if you extract, right, so I'm assuming that I have a plane wave instance here, right? This is my plane wave instance, U instance, with direction alpha. And I'm going to extract the phase of the incident field in this representation. Eta is equal to eta k alpha dot x times eta slow xk. And what is plotted in these figures are the real and imaginary parts of this slow density. It is called the amplitude, right? So, right, this is quite in agreement with our physical intuition that the density generated on the boundary of the scatter must oscillate similar to the incident field. There are, as you can see, there are two issues here. With increase in k, there are some boundary layers, and right, these boundary layers are focusing at 2 points, around 2 points, with increase in k, and those 2 points are exactly the points. If you look at this scatter on top and on the bottom of its surface, those are called the shadow boundary. The thickness of these boundary layers are of order k to the power minus 1 or 3. So going back to our integral representation for eta, equation 2 from the bottom, if we extract the face of the instance, right, using the equation on top, we can write this integral equation in terms of the new unknown, the amplitude eta's law, in this form. And this is quite good, except that the kernel here, eta k alpha y minus x times the normal derivative of the Green's function, is still high loss oscillator. So this is a challenge for the evaluation of a high loss rate integral. There are some quite advanced methods for evaluating such integrals, but the real challenge is, of course, to derive write some rigorous error estimates in your numerical approximations. Going forward to the Sandhart problem, the situation is similar, right? So you assume a plane wave instance, for instance. You extract the face of the incident field, plot your slow density, mu slow in these plots. You see that the solution dies off in the shadow region, maybe in a slower way, but it does with increasing k. And similarly, you can play the same game. You start with the integral equation for your unknown mu, the total field, and then extracting its face, you end up with a similar integral equation. Still, the kernel is high loss oscillator, right? So these are basic observations for an engineering implementation, but from a mathematical point of view, the question is, can you actually solve these integral equations in a manner that the number of degrees of freedom you use, for instance, if you are discretizing the boundary of the scatter, the number of discretization points, right, the aim is to make sure that the number of the discretization points does not increase with increasing k. Can we actually generate such a discretization? And if you do so, then the arising linear system out of that will again not depend on k, its size. So therefore, you can solve this problem for any k, independently of how large or small or k is. And that's the essence of these problems. So in this direction, right, starting exactly 20 years ago, some numerical methods have been developed. The first one was due to Bruno, Guzen, Monroe, and Reitik in 2004. Based on a combination of main principles, and the results they obtained was displayed that the number of degrees of freedom is fixed. It need not increase with increasing k. And a few years later, some other methods came out, but these three methods up here included no analysis. It was just an observation, just the right, the algorithm implementation, and we are happy, but no rigorous analysis. The first rigorous analysis was performed by the algorithm down there by Dominguez, Graham, and Smishlev in 2007. They utilized a Galerkin boundary method with a special treatment around those boundary layers, right, that I have shown you. And they proved that the number of degrees of freedom to maintain a fixed accuracy, so you want to say obtain 5 digits of accuracy in your solution, then the number of degrees of freedom should increase in proportion to k to the power 19. So still, the problem is then as depicted in these implementations without analysis, can one attain, can one derive a rigorous numerical method with a rigorous analysis which performs all one, basically. So with my MS students, actually, a few years back, we developed two classes of Galerkin boundary element methods, which I'm going to talk in a bit detail shortly. We generated Galerkin boundary methods, and we show that these methods demand the increase of the number of degrees of freedom proportional to k to power epsilon for any epsilon positive. So epsilon could be as small as you like, right? So this is almost order one, right? These two methods are almost order one, but still, as you see, they do not answer this O1 order one holy grail, right? It was still an open problem. So to talk about the details of these methods, right, I'm going to write my scattering problem, right, in this form. I'm going to assume that the equation RK eta equals FK is your favorite integral equation formulation for the unknown eta, right? It is the normal derivative of total field in the Samtsov case. And then, right, the Galerkin formulation of this problem, right, in its weak form is written down here. And then, right, using Say's lemma, right, the solution of the Galerkin equation, eta hat, right, the distance between them in the L2 norm, is bounded by beta k or alpha k, continuity and coercivity constants of the integral equation you are using, times this infimum. And this infimum, as I'm going to talk about, can be approximated using classic techniques from approximation theory, right? So this stability constant for certain geometries, as shown in this paper by Galkowski, Müller, and Spence, grows proportional to k to the power 1 over 3 for the combined field, the so-called combined field integral equation. I didn't write it here. So there is this coefficient beta k or alpha k, which grows k to the power 1 over 3. So this infimum, in order to obtain an O1 method, should beat that, right? It should be of order k to the power minus 1 over 3. Right, that's an additional challenge in this Galerkin approach. So the idea here is that you have I'm writing eta instance, but this is not eta instance, u instance. U instance xk is my plane wave, e to ik alpha, that x alpha is the direction of the plane wave. And then in the next line in green, eta xk, right, is written extracting the face of its face using the face of the instance, e to ik alpha dot x. So this gives rise to the envelope eta's law. And right, we are trying to approximate eta, what is in green on top, by eta hats. So because it has this factorization, the approximation should also have a similar factorization, exactly the same factorization. So this motivates you to generate your approximation spaces xk, written in green, as the oscillations in the instance e to ik alpha dot x times yk. So this, as you see, Say's lemma then is written down there, reduces the problem from approximating eta by eta hat to approximating eta's law by mu hat, where mu hat belongs to an appropriate approximation space, right? So the question is then, how do you generate these approximation spaces yk, right? this generation, in order to have a scheme which is frequency independent, should of course depend on the asymptotic behavior of the solution, right? And this demands going forward, by the way, going forward. So right, as I have written, you have an approximation problem for that infimum. And from classical approximation theory, if you are using approximations on polynomial spaces of degree d, then this approximation is bounded by d to the power minus n times this semi-norm of f. And this semi-norm involves the derivatives of your function f, right? You are trying to approximate f by polynomials. And this infimum from classical approximation theory is known to be bounded by d to the power minus n times the semi-norm, and this semi-norm involves the derivatives of f. Going back to the infimum up there, then, what we need to derive is bounds on the derivatives of Eta's law, right? Eta's law is the unknown. You have to derive derivatives on the unknown Eta's law. This takes us to the asymptotic behavior of this amplitude Eta's law. This was initiated by Melvin and Taylor around 1985. So on the eliminated region, this density is known to have a classical asymptotic expansion, but right, there are 2 points. If you look at the scatter on the top right, there are 2 points at the bottom and on the top of the scatter where these rays are tangential to the boundary. So these asymptotic expansions written in here, Eta's law is the summation of APQs. Right, this was derived by Melvin and Taylor using Fourier integral operators with some geometrical folding relationships. And APQ here are given in terms of this function, right? Psi called the Fox function, right? Here the function z is positive on the eliminated region. The eliminated region is on the left. If you look at the scatter, it is on the right. The shadow region is on the right. And right, shadow boundary points are the points on top and at the bottom. So this Fox function has some asymptotic properties. The first property that it is a sum of CJs, tau to power 1 minus 3 j, is valid basically in our setting on the eliminated region, and this rapid decay is valid in the shadow region. All right. Let me skip this part about the Sandhart problem. This is a more right. The asymptotic expansion in this case is more complicated. It involves area functions and area operators. But anyways, the basic idea is the same, right? The asymptotic behavior of the solution is changing from a classical asymptotic expansion to asymptotic expansions with folding canonical relationships around the shadow boundaries, and then they decay fast in the shadow region. Right, for our approximation spaces, these derivatives written down there sound soft and sound hard. Right, right, these estimates involve the derivatives of these slow densities. And these approximations are important for approximating that infimum. So this was derived for the soft case by Dominguez, Graham, and Smichler in 2007. And recently, we also did the same thing for the Sandhart case. So going back to, right, so what is essential, if you look at the Sandhart case, there is this function WSK. It is written up there, right? Equation 4 from the top. It has the form k to the power minus 1 over 3 omega s, and omega s is defined in the equation on line 3. So if you look at its graph, omega is vanishing at the points T1 and T2, and T1 and T2 correspond to those 2 points where the rays are tangential in your parameterization. So as you see, when S in WSK, when S is equal to T1 or T2, omega of S is equal to 0. So in these approximations, omega SK, when S is equal to T1 and T2, is of the form k to the power minus 1 over 3 raised to the power minus n. So it is blowing up proportional to k to the power n over 3, right? The nth derivative at the shadow boundary points are blowing up with increasing k as k to the power n over 3, n is the number of derivatives. So this blow up in the derivatives around the shadow boundaries signifies that you have to refine your approximation spaces precisely around the shadow boundaries. So going back to these two methods with my students, right? So again, I'm taking a convex scatter. It need not be a unit circle, or right? It can be any convex obstacle. I'm considering here an incidence alpha coming in from the left. And as you see, there is this eliminated region, right? There is this eliminated region on the left. There is this shadow region on the right. And there are two shadow boundary regions, SB1 and SB2 on top and bottom. And there are 4 pink regions, which I will call as transition regions. So what we do is, it's written in here, but what we do is, right in this partition of the boundary, we are basically subdividing these pink regions into subregions, the number of and size of which depend on k. So they increase, and actually with increasing k, the blue parts of the right, the blue parts described here fill out as k goes to infinity, fill out the entire boundary. They shrink, or the remaining parts shrink down to the shadow boundary points, basically, in these representations. And then what you do after you divide these pink parts into subparts, you define your approximation spaces on each one of these subregions in the form A sub j, right? These are local approximation spaces. A sub j, 1j stands for the characteristic function of the region you are restricting yourself to. E to ik alpha dot gamma is the right, is simply the incident field, and then you modulate these using polynomials of degree dj. And then your Galerkin approximation space is the direct sum of these 4 M regions, basically. And if you apply this to the Sandhart problem, right, this Galerkin boundary method to the Sandhart problem, the relative error is bounded in this way. What is in red, M, in these approximations, is the number of subregions you are using. As you see, the number of subregions, as the number of subregions increases, the exponent of k decreases, right? It decreases, right? It decreases in both approximations. Here, these are the Heaviside functions in the Sandhart case, and also the Kronecker function. And beta k over alpha k is the right. This is this analysis is independent of the underlying integral equation, so long as it is continuous and coercive, right? Continuous and coercive formulation. This second method is more recent, until 2019. Rather than using several, right, 4 M approximation spaces, we are only using 6 approximation spaces, but we utilize a change of variables to represent the integrals involved using some explicit formulas that depends on K. And we define the local approximation spaces in this form. Around the shadow boundaries, as you see, we don't do any change of variables. And there is no blue region here. So all pink parts are going to be termed as transition regions. There we utilize phi inverse, where phi is a K-dependent change of variables. In a moment, I'll show you explicitly what they are. And then you define your Galerkin approximation spaces in this form as this direct sum. And these are the area stability you obtain, right? So as you see, this is very nice. Aside from beta k over alpha k, you have logarithm k to power n plus 1 over 2. The n depends on the number of derivatives you are using. These are nice, but still, right, these error bounds are not of order 1, right? So I am not saying that the relative error is bounded by a constant. And that constant decreases with increasing n. I'm not saying that because beta k over alpha k in the soft case, for instance, increases proportional to k to power 1 over 3. So, right, these are the summaries of the estimates I have shown you, but then you work out these estimates, right? There are basically 2 or 3 types of estimates, if you want. You work these out, and then you ask the following question: Can I choose D and N in such a way that these error bounds are as small as possible, or they grow as slow as possible? That is doable. And this gives you that increasing the number of degrees of freedom proportional to order k to power epsilon is sufficient to fix the error independently of the frequency. So we are almost at order 1, but not yet. So I don't want to go into the details of this slide, but the essence of this slide is, right, you can actually attain order 1 solvability if you do the following. So, right, there is Eta's law in red with its asymptotic expansion, summation over PQ of APQs. APQs have certain forms, and if you know A0, right, the smallest term in the asymptotic expansion, which has the largest exponent in its expression in terms of the power of k, if you know A00 explicitly, and if you incorporate it into your integral equation formulation, then the method is of order 1. And this was never done before. So this is more general, basically. Rather than O1, this takes you to, if you can compute, of course, these APQs for sufficiently many values of P and Q, then this analysis shows you that you obtain, right? So these are similar error estimates, except that there are these additional blue terms here. These nu L depend on the number of terms you can explicitly compute in the asymptotic expansion. The more you compute, the larger nu L, the power of k. So it kills beta k over alpha k. Not only that, your solution, right, numerical approximation, converges faster with increasing k. So you get the error decays. Here is, without using any term in the asymptotic expansion, here are some implementations for the circle and ellipse. Right, the directions of the incidence in the circular case is from the left, and you see for the ellipse, it's a little inclined. And these are the numerical results we get. As you see, the numerical methods seems almost independent of k, right, with small variations. But as you see, as the number of degrees of freedom increases, the convergence slows down. This is related with all the methods in this realm, because we are using polynomial approximations, and for instance, right, the polynomial degrees are increasing from 5, 10, 15 up to 30. And when you have those, the right conditions, condition numbers of the linear systems exceed numerical, right, exceed the limit of numerical precision. So that there is some stability issue because of the use of polynomials. I'm not showing here, but you can also use trigonometric polynomials, in which case this problem does not arise. And the condition numbers of the linear systems are much better behaved. These are some implementations for the Sanhar problem, so similar behavior, although the error here is larger because if you remember from the plots, the solution was decaying slower in the shadow region. That's some technicality here. So next, I'll move on to very quickly to the multiple scattering problem. So as you see, I have in this particular setting, I have 3 obstacles. And what I'm comparing here is I'm taking again an incident field, this time with direction d, right? U inc is e to ik d dot x. Then I'm writing my eta as eta slow times e to ik d dot x, the same thing, and trying to solve this integral equation. So what is plotted right on the first line of these figures is if I have just a circle here, but these are the real and imaginary parts of your solution. And what is plotted on the 3 figures at the bottom is if you have 2 circles, just like this, these are the real and imaginary parts of the solution. And as you see, there is some pollution, significant solution on some parts of the scatter. These plots, in both cases, are restricted to the smaller circle. Okay, and right, this pollution, if you consider the parameterization of your circle, this pollution effect is corresponding to the region where the 2 obstacles are closest to each other. Okay, there is the rays there are going to multiple scatter, right? They are going to, if you have if you are doing a ray tracing, the rays would be bouncing back and forth between the obstacles in those regions, and those regions are, for the smaller obstacle, are corresponding to these pollution effects. And then as we did for a single obstacle, we extract the phase and we plot now eta slows. You see, for a circle, eta slow is nice, except for these boundary layers, for which we have very good numerical methods. But for the case of 2 obstacles where there is multiple scattering, this phase extraction works on some part of the boundary, but it doesn't when on the regions where there is multiple scattering. So how do we resolve this issue? Okay, but this is the integral equation we should solve. Eta here in blue is defined on the boundary of omega, right? Omega is written at the bottom of those scatters as the union of these 3 omegas. So this boundary here has 3 parts, for instance, here. So then you can write this integral equation in component form. Right, restricting your operators as written down here, right, are ij, eta j is defined in this way. All right. So what is our ij doing? Eta j in this, right? So let me take this integral to the top of the screen. Eta j is defined on the boundary of the obstacle omega j. You are integrating There is a mistake here. So this should be mapping, right? This should be mapping. This must be eta I, basically. So this is mapping your solution from one obstacle to the other obstacle, basically, right? And then you look at the diagonal, right? This component form has a diagonal written down here. You multiply this integral equation written in component form with the inverse of this diagonal equation. And right, so this when this is done, you get this component form of the alternate right, of this alternative solution. And what is really happening is if you look at right, invert the diagonal I write. So let me carry out to the Tij is this must be I sub I, the identity operator, not I sub 1. I sub I, RRI inverse Rij. So Rij is mapping the solution from the boundary of ith obstacle to the boundary of the ith obstacle, and then you, with this inverse, you are solving the scattering problem, right? Gi is the solution of this must again be I sub I minus RII inverse Fi. G sub I is the solution of the scattering problem as if the only obstacle in the medium is the ith obstacle. So we can therefore write this equation, written down there in components in this form: identity minus T eta is equal to G. And right, if you have such an equation, its solution is formally given by the Neumann series. I'm not talking here about the convergence of the Neumann series in this talk, but years back we have also derived rate of convergence formulas for the Neumann series. For instance, if you have only two obstacles, looking at the figure up there, the rate of convergence depends on the distance minimizing points between the two obstacles along with their curvatures there. Right, so you can actually derive asymptotic rate of convergence, but here in this talk, I'm not going to look at that. I'm just going to look at this formal series. I'm not going to try and evaluate this until infinity. I'll just look at how to compute the terms in the Neumann series, and my final focus will be on the computation of the infinite tail in just one solve. Right, the idea is to evaluate T2 mg's for a sufficient number of m's, and then look at the remaining infinite tail in a different form. So actually what you can do is you can, looking at this formal Neumann series presentation, you can then dismantle this Neumann series into the superposition of these formally again, of the solution of these integral equations. If you compare these two integral equations, the first one, right, involving eta 0, involves integration on omega 0, right? And as you see, this integral equation does not depend on the other obstacles, which means that you are solving the scattering problem as if your obstacle is the only obstacle in the medium. It's the single scattering problem. And then if you look at this second integral equation on top, the right-hand side is different, but this is nothing but twice the normal. The right-hand side is twice the normal derivative of the scattered field evaluated on your obstacle omega m. All right. So this then tells you that you start with this integral equation of the second kind, and then you reduce the solution of this integral equation to the right, to the superposition of the solution of these integral equations. There are infinitely many paths, as you can see here, that you can follow. The problem is then how do you solve these integral equations involving eta 0 and eta m? Exactly as you did for a single obstacle, which corresponds to eta 0 here. You find eta 0's law by extracting the phase of the instant field, right? Phi 0 is d dot x. D is the direction of your plane wave. And then you play the same game. Right? You extract the phases of eta m's. Phi m's are given by geometrical optics. What I mean by geometrical optics is are given by ray tracing. Here's an implementation in that direction. So I'm looking at a two scatter configuration consisting of two convex obstacles. My instance is from the left, and then I start from the scatter omega 1, reflect to omega 2, come back to omega 1, reflect to omega 2, and so on. All right? So when m is equal to 0, I am on my obstacles omega 1, and you see the plots on the top row for eta 0, eta 0 slow, and the corresponding phase function. Right? And I'm taking m to be 5, which means that I have bounced back and forth between omega 1 and omega 2 5 times. And these are the plots of the densities, their slow versions, and the corresponding phase functions. And also, right, at the bottom, m is taken to be 20. So in these particular problems, numerical implementations are very important because it gives you ideas about the analysis of the problem. As you see, if you compare the plots for m equals 5 and m equals 20, they look very much alike, except that as you see the phase function in the case m is equal to 5 and m equals 20 are shifts of each other, constants. Shifts of each other, right? They look like that. So you can actually prove this. That, right, the phase corresponding to m equals 20 is a constant shift of that for m equals 5 with a perturbation bound that depends on the number of reflections. Right? It's the case in proportion to the number of reflections. So the solutions are also similar, but as you see, there is 10 to the power minus 4 in the case m equals 5, and 10 to the power minus 8 in the case m equals 20. So this actually motivates the following. Right, so the solutions also have boundary layers around similar regions and so on. So this motivates you to generate approximation spaces based on this stabilization property. Okay, so these are similar plots for the sound or hard problem. The observation here in this case is under certain geometrical case assumptions, the associated waveforms, right? This is your plane wave in the first plots. Then you consider a certain sequence of scattering obstacles in this particular configuration. And as you see, all the waveforms are convex. These are computed using some Fourier series and so on. Right? These are quite maybe exact up to 10 digits. Okay, so let me now move on in the remaining 0 minutes. So I'll just take 2 more minutes. Let me move now to the Ray-stabilized Galerkin boundary methods. This is ongoing work. So right, this is our integral equation formulation. And then this is the formal series, Neumann series presentation. And usually naively, what you would do is you would approximate this Neumann series with a finite partial sum. The computational costs of this Neumann series, when there are two obstacles, n is equal to 2, is requires you to solve two M0 integral equations. But when n is greater than 2, it requires you to solve this many integral equations. It grows very fast, so you don't want to solve too many single scattering problems. That's the reason why we want to be able to compute the infinite tail. We don't want to increase the cost. So, plugging this partial sum into your original integral equation on top, identity minus t eta is equal to g, you get this integral equation for eta m0, right? Eta m0 is defined as what you want to compute, eta minus the partial sum which you have already computed. So eta m0 is really the remaining infinite tail. It satisfies a similar integral equation as you see. Identity minus t eta m0 is equal to t to m0 g, which I'm going to call g m0. And so it is written down here, that integral equation. So I want to solve this integral equation, but I don't want to use Neumann series anymore. I want to construct an approximation space which is fixed. I'm going to solve it, and I'm going to add that to what I have already computed as the partial sum of my Neumann series, and that is going to be my approximation to eta. Let me move on. Okay, so I'm taking M0 to be 10 here, right? M0 to be 10 here, two obstacles, and plotting the real part of eta m0, imaginary part of eta m0, computed using the solution of the associated integral equation here, numerically. And then I want to know, exactly as I have been doing before, in order that I can solve or compute eta m0 in a manner where the number of degrees of freedom is independent of k, I need to know its phase. There you go. I can also compute a phase for this one, right? Here's the phase on the left and the real and imaginary parts of the associated slow densities. So in the same way, I can generate Galerkin approximation spaces for this problem up here and solve this problem in a manner that requires the increase of the number of degrees of freedom proportional to order k to the power epsilon if I don't have any term in the expansion. But if I include one term, it is so forth. So this is the essence of the talk. I was planning to talk about scattering amplitude, time permitting. It didn't happen. So I want to say, listen.